Okay, we'll get started. Okay, is there any questions before? Otherwise, I'll just sort of jump in where we left off. Okay. Okay, so just to review, I'm just going to add to the notes from yesterday just because I wrote a bunch. So we talked about the SSL handshake. So here it is in all of its glory. And then I want to show you a couple attacks on it. The attacks don't work today. Okay, they're going to assume they worked at a point in the time, and we'll like sort of try to pinpoint what was it that allowed the attack and then how to fix it. So this is something when you design protocols, you don't always get it right the first time, and so sometimes you have to look at things. So the first attack is called the padding oracle attack. We're going to assume that the whole handshake happens. There's no problem at all with the handshake. Okay, so there's nothing with the handshake itself. So at the end of the handshake, Alice and the server have keys. They have an encryption key. They have a MAC key. And in this case, we're going to use both encryptions and MACs. The encryption is going to be in what's called CBC mode. CBC mode looks like this. We're going to come back to this picture later because we're going to have to understand it a bit to see what's going on. But generally speaking, it's just a way of allowing you to encrypt something that's more than a single block. We're going to assume that we're going to use MACs. And specifically what we're going to do is we're going to MAC and then pad and then encrypt all of that. Okay? That's not the only way that you can use MACs. You could also encrypt it first, pad it and encrypt it, and then put the MAC on the ciphertext as opposed to the plain text. Okay? So this will be another sort of ingredient of what makes the attack work. Then we have to deal with the fact that your messages aren't always like perfect chunks of 256 bits. So the block cipher expects 256 bits to come in. So you're going to have some padding that you're going to have to do to fill up the blocks. And so the padding that was proposed is very simple. It's just figure out how many bytes you want to pad. Whatever that number is, just repeat it that many times. Okay, so for example, here you repeat the number 5 times. And then the last thing, and this is actually where basically the mistake was, I mean, everything kind of contributed to it, but this is the part that was done incorrectly, is you could, if you receive a ciphertext and you try and decrypt it, and it doesn't work, you want to say there's an error, and you're going to ask the sender to send it again. Okay. Now there's two kinds of errors. The first error is you could download it, you could decrypt it. There won't be an error in the decryption itself. So with CBC mode decryption, you can always decrypt something. You'll take your ciphertext, you'll put it through, you'll get back something for the plaintext. Is it right? Is it wrong? I don't know. You're going to have to figure that out by looking at it. But it's not like the decryption itself can't fail. It will always give you some answer. Okay. There are encryption modes that will fail at the decryption time, but this is not one of those modes. Okay. So you'll decrypt it, and then now what you need to do is you have to figure out where the message ends, where the MAC ends, and you don't really know that because you don't know the size of anything. So what you're going to do is you're going to go to the very end, and you're going to look at the last byte. And it's going to tell you, say, 5, and you're going to say, okay, that's a padding byte. And so that means I'm expecting 5 padding bytes. So you'll go over, you'll check all 5 of them. All 5 of them should be 5. Okay. If they're not, let's say that you get 0504, 05, 05, 05, you know that there's something went wrong in the decryption. Okay. So right away you can throw an error. And so the error that you would throw is a padding error. Okay. Now, if the padding was okay, then you now know where the MAC ends. And the MACs are always constant size, so you always know how big it is. So you can pull the MAC out. Sorry?
How can I know if there is an error?
In the padding?
Yeah.
Okay, so the algorithm is you look at the last byte,
Okay.
and it tells you, say it's 05. That tells you that there should be 5 bytes of the number 5.
So what if the first one, what if the last byte's wrong?
So if the last byte is wrong, then you always want to throw an error, period. Right? You know, like if it's only wrong because it you should be throwing an error. Yeah.
But if you
So if the first one is,
would you assume that there was 5, would you assume there was only 4?
sorry, so say again. So the,
If you're checking the last one and it says 4, would you assume that there's 4?
yep, yeah. So maybe I didn't explain it well, but like you'll look at the last byte and
Say there's 5 and the last one.
I'll give you 2 examples.
Sorry.
So let's say I look at the last byte and it's 3, then I'm going to assume that there's going to be 3 bytes of 3, and then I'll move over 40 bits or whatever the size of my MAC is, and I'll decide that all the bytes here are part of the MAC. They're not part of the padding. Does that make sense? Yeah. And if I look and I see that it's 05, then I would expect 05, 05. But let's say I see 01.
That means,
Oh, I see.
okay, so
Yeah?
it's not
That's an error, right?
That's a padding error, right? Because now I know there's a problem with the padding. I don't even know where the MAC ended, because maybe this is right and this is wrong. Like I don't know,
But there's mismatch.
but there's a mismatch. Yeah. So the padding is incorrect at this point. Does that make sense?
Yeah.
And if the last one is different, also it's an error, right?
If the last one is which?
Same as the example, the previous example.
That means the last one is 4 and the previous
For
one is
example,
5,
here,
5,
if,
5, like
if the
this.
last one is 0.4, it's an error, right?
So if the last one's 04, it's an error, but you don't know it until you hit the 05 here.
Okay.
Because you're thinking there's 4 bytes of 4, and then you see the 5, and then you're like, okay, that's a
And in
padding
this
error.
example,
Yeah.
it's correct.
This is correct padding. Yeah. Does that make sense?
Yeah.
Okay, be 100% about this, because you're not going to understand the attack if you don't get this padding thing. Okay, so you look at the last byte, and then you're expecting that to be repeated that many times, and if it isn't, then you throw a padding error. Okay, if the padding is fine, then you extract the MAC, and then you check the MAC against the message. So you run the message through the MAC algorithm and compare the output to what's sitting here. And if it matches, then decryption is good. And if it doesn't match, then there's another kind of error, which is a MAC error. Okay, so the padding was okay, but the MAC, there was something wrong with the MAC. And so what SSL would do is it would tell you which of the 2 error conditions occurred. Okay, should it tell you which of the 2 error conditions occurred?
No.
So it's telling you something about the plain text. Even though it's about MACs and padding, it's not about the message itself. It is telling you something inside the encryption, right? So it's first decrypting, then it's learning what it is. So it's leaking a little bit about what's happening inside the encryption. Normally with encryption, you don't want to leak anything about what's inside the encryption, okay? Other than maybe just like, yes, it's right, or no, it's wrong. Because you do need to ask for it again if it's wrong, okay? All right, so in this attack, we're going to exploit the fact that we can tell the difference between these 2 errors, okay? And because we can tell the difference between the 2 errors, we can actually decrypt things. Sounds crazy, but it will allow us to decrypt things, okay? So this is, okay, so first thing, let's take a close look at CBC. And here I'm just focusing on decryption. Okay. I'm an adversary, I'm in the middle. What do I see? I see the ciphertext, right? I don't see the plain text. I don't know the key. I have no knowledge of the key. Can I change the ciphertext if I want to?
No.
Okay, why not?
You could.
Okay, I could change it, right? What's going to happen if I change it?
It won't be the same message.
Okay, so the plain text is going to get messed up. And because the plain text is going to get messed up, what's going to happen? There's going to be an error, right? Maybe a padding error, maybe a MAC error, but like it's not going to get through, okay? But can I still do it anyways? I can still do it, okay? So here's what I want to do. I want to take the last byte of the second ciphertext here. I'm just going to change it to 00 or 01 or something like that, okay? What's the consequence of making that change?
The next one also will change because it gives a feedback.
Okay, let's go to the plain text here. Does changing this byte have any impact on this at all? No.
The second
Okay.
and the third one.
Okay. So when I decrypt it, my first plain text block is fine. Okay, there's no changes at all. Okay, so that's good. What happens to the second plain text block?
It changed.
Okay, and where? Okay, so one thing you should know about encryption, if you haven't taken 6110, is there's a thing called the avalanche effect, which basically says if you change one bit of the input, the output completely changes. Okay, so the tiniest, like just a single bit difference will result in a completely different looking output. Okay, so the encryption function or the decryption function here is like a random function. So if I change this, I'm changing, the whole plain text is going to change. Okay, so I'm just denoting that as pink here. So this whole thing is going to be garbage. Okay, what about the third block?
Yeah, it's also gonna be messed up.
It will change. But not in all bit. Because the output is like XOR with the feedback. So not all the bit will change.
Okay, so what will and what won't?
The last one. Because the ciphertext, if the last bit is modified, so the last bit of the plain text will be like distorted.
Okay, so the ciphertext, I didn't change this. We all agree?
Yes,
So the decryption is going to be fine. So the output that's sitting here
it's good.
is good. It's the same. Okay, but then what I do is I XOR
Yeah.
it with the previous round, and because I changed the previous round, it's going to change. How does an XOR work?
It's the same bit.
So you just go like bit by bit, and you just XOR each bit together. Okay. So if I'm changing only the last byte here, then only the last byte of this is going to change. Okay. So this is what I'm going to do. So I'm going to change one byte here. I'm going to destroy block 2. I'm going to destroy the last byte of this plain text, but the rest of this plain text is good, and the first plain text is good, and if there's a whole bunch of blocks before it, they're all good too. Okay?
Why only the last one changed?
So the XOR here is an operation that looks like this. Okay, so this, we'll say, is what's coming out on the wire here, right?
Yeah.
It's correct. Every byte for byte, it's exactly what should be, right?
Okay.
Yeah? The other input to the XOR we can write here. And it's just a copy of whatever the ciphertext block was. And I changed the last one, right? So these ones are all fine. And then this one is messed up.
Okay.
Yeah. And then XOR is the kind of operation that it's not like something, you don't take the whole block and combine it with the whole block. It's like a bitwise,
Yeah.
one by one kind of operation. Yeah.
So because we only changed the last one, so when we do the XOR operation, only the last plain text will be changed.
Correct. Yeah. The last byte of the plain text will be changed. Yeah. Or bit, if you flip the last bit, whatever you flip here. Yeah. So a byte being more than one bit. Okay, so far? Okay.
So every byte XOR with the one. Okay.
Yeah? Okay, okay. Okay, now I'm going to write out the decryption in, actually I'll write it here, and then later we're going to use it, but I'll just write it here in equation form. So this is exactly the same thing. It just says that the ith plaintext block is decryption under the key of the ciphertext, the ith ciphertext XORed with the previous ciphertext. Okay, so that's the equation, and then C0 equals IV. So the first time you decrypt, you don't have a previous ciphertext block. And so that's what the initialization vector is for. Okay, so here's the attack.
This is the same padding oracle attack?
Yeah, so this is all part of this. Everything from here is, this is the actual attack itself, yeah, assuming all of this. Okay, so the attacker will change. I'm going to write Cn minus 1. That means the nth minus the second last block. Okay, so that means this block. And because we're just changing the last byte and not the whole byte, I'm just going to use square brackets and say 15. Okay, so that means the last byte of that block. You don't really have to, this notation is not that important, but I want to be precise about it because we're going to recurse on this. Okay, so the attacker is going to change this. So visually, they're just changing the purple thing. Okay, what do they change it to? They're just going to pick a value. Okay, they're going to actually try multiple values here. But first they'll start with 0, then they'll do 1, then they'll do 2, then they'll do 3. Okay, all right. So they'll write in 0. And 0 will be a counter. Okay, then they're going to submit that to the server, and the server is going to tell them one of two things. Well, three things. They're either going to say, great, I decrypted that, I'm happy. I tried to decrypt it, it didn't work because the MAC failed. Or I tried to decrypt it and it didn't work because the padding failed. Okay, those are the three outcomes that we could see. Okay. All right, will it ever return, I'm happy, I decrypted it, there was no problem? Okay, if you make a change to the ciphertext, that should never occur. If that occurs, that means you broke the MAC. You found some other value that produces the same MAC even though you don't know the key of the MAC. Okay, so you'll submit. And then you're either going to get success, but this basically will never happen. So I'm going to write negligible. Two, you're going to receive padding error. Or three, you're going to receive MAC error. Okay. What can you tell me about the value of this byte here? So this byte, what is this byte relative to what it should be? Let me put it that way. So let's say that this byte originally was, I don't know, 10. I change it to a 0. Okay. The difference between 0 and 10 is going to be the same as the difference between this plain text bit and what it should be and what it was. Okay, that's maybe not the best explanation. Let me try to explain it a different way. Let's look graphically at this picture. Okay, what I do is I make a change. It's going to destroy the middle block, and it's going to randomize the last byte here. Okay, so this byte is just going to go to a random number. Okay, so let's say that this gets replaced with, I'll make a copy of it down here. This is important to understand. So I have M. I have maybe a bit of M. I have the MAC of M. Then I have padding. I'll describe it as 5. Okay. And because I attacked the ciphertext, I'm going to mess up this whole ciphertext block. And I'm also going to mess up this block here. Okay?
Does all the padding should be the same?
Yeah, all the padding should be the same. Well, sort of. Well, let's go through. So there's one corner case that we're not thinking of. But yes, generally it should be the same. Okay? Let's say that this happens to go to the value 7. What would happen? Would you say that that's a padding error or a MAC error? So I would expect 7 to repeat it 7 times. I look at the second byte, and it's a 5. So is that padding okay?
No, bad.
It's bad, padding error. Okay. What if this is a 10? Okay. What if it's a 3? Okay, so these are all padding errors. What if it happens to stay at a 5? Then it's okay. Then what's going to happen though? When I run the MAC, this is all changed. I'm going to get a MAC error. Okay. Will I ever see a 5?
Maybe or may not.
Basically, if I don't change, the only way I get a 5 there is if this is the original. Okay, there's no way I can get a 5 here. If I change this, I'm going to change this. Okay, so if originally it was a 5, the only way I can get a 5 is by leaving this ciphertext alone and not changing it. But if I don't change it, then I didn't attack the system. Okay, so this won't happen by accident. What if I get this? Yeah. What if it gets flipped to 0, 1?
The last one?
Yeah.
Then it's a
Padding.
padding error.
Padding, yeah.
Okay, so what does 0, 1 tell me per patty? It says I expect 1 byte of 1. So I go to the second byte, and what am I expecting to see here?
Nothing.
One.
Nothing.
0, 1.
Because there's only one byte.
Okay, so
There's only one box.
okay. So if I go here and I'm expecting a 0, 1, well, then I have actually 2 bytes of 0, 1, right? So if I have 2 bytes of 0, 1, it's not a padding byte anymore. Okay? So if I have a 0, 1 here, then I don't care what this is. It just means that the MAC came all the way up to this last block, and I padded it with a 0, 1. Okay? So 0, 1 is valid padding. There's no problem with this. Okay? So this is valid.
Can you repeat that?
Yeah.
Could you repeat that one, please?
Yeah. Okay. So let's think about let's write out all the valid paddings. Okay. Not all of them, but let's write out a bunch of them. Okay. So let's say I want to pad 3 bytes on the end. What does my padding look like? So 0, 3, 0, 3, 0, 3.
Yeah.
Okay. What if I want to pad 4 bytes?
0, 4, 0, 4, 0,
4 times.
4 times.
What if I need to pad 2 bytes?
0, 0, 0, 2. 0, 1 would just be 1.
Okay. And what if I only need to pad 1 byte? So like I'm almost filled up, but I need 1 byte
Just one
to
byte.
fill it up. Then I'll just put in 0, 1. Okay, so these are all valid paddings. Yeah, and then you can keep going. And anything that's not one of these, right, won't be valid padding. Okay, so if I flipped a 0, 5 to a 0, 1, I actually have valid padding. Okay,
Means there is no error.
there's no padding error.
Padding.
Okay, is there going to be a MAC error? You bet, because I messed up this whole block here. Okay, so what I'm going to do is I'm going to see the padding is valid, and I'm going to get a MAC error instead of a padding error. Okay, so yeah.
Is that the only way you can get a MAC error then? Like you only need to have one block to get a MAC error?
Yeah, so a MAC error will happen anytime you make any change at all to the ciphertext, there's going to be a MAC error. That's sort of what a MAC means. A MAC means basically it's either an exact copy of the plain text, or if there's any tiny mistake anywhere, then it's not gonna go through. Yeah.
So how can we detect a MAC error?
Okay, so what I'm telling you is that the software is going to tell you. So the attacker is going to do this. They're going to change this byte. They're going to submit it. And then the server is going to say, sorry, I couldn't decrypt that because the padding was bad. Or the server is going to say, sorry, I couldn't decrypt that because the MAC is bad.
Okay, so if the adversary changes anything, the system will detect the MAC error directly, right?
Yeah. So it's going to detect both kinds of errors, but it's going to tell you which of the two errors.
Okay.
And that's the information that we're going to use.
And we can have the two of them, right?
Yeah. So what we're going to do is we're going to change this to 0, 0. We're probably going to get a padding error. Okay. But if we happen to get a MAC error, then we know whatever change we did here, it made a 1 here. Okay, so I know I flipped something around here. I don't know what it did. It went through a bunch of stuff. But whatever happened, a 0, 1 came out here because that's the only other option. That's the only way I get a MAC error. Does that make sense?
Yes.
Okay, so I figured out a value I can put here, a counter value I can put here, so that a 0, 1 will come out here. Okay, yeah.
Out of curiosity, is there any way there at the end of the ciphertext there is no value at all?
No, so what would happen is you would round up to the next block. So let's say that your message cleanly fit because the person decrypting has to parse out the padding. There's no way to denote that. And so what you would do is you fill the next block with, 15, 15, 15. Yeah. So it would be kind of a waste, but yeah, that's how you would do it. Yeah. Okay, so what I'm going to do is I'm going to just guess at a value for the last byte of the second last block. If it's a padding error, I'm going to go back and I'm going to increment my counter. Okay, so CN minus 1, 15 plus plus. So I'll try 0, 1. And then I'll submit it. I'll probably get a padding error again. Then I'll try 0, 2. Then I'll try 0, 3, 0, 4. And all of a sudden I'll hit 0, 8. And for whatever reason, now all of a sudden I get a MAC error instead of a padding error. Okay? And so that told me that whatever change I made, it resulted in a 0, 1 at the end. I don't know what I'm going to do with that information yet, but that's what's going on. Okay? So now what I know is CN block 15 equals 0, 1. Okay, so I know that this is the case at this point. Okay, can I use that somehow to decrypt the ciphertext sort of block by block? So it turns out I can. I know that what change I'm making here results in a 0, 1. Okay, and so what I can do is I can figure out what this was before I made the change. And because I know what it was before the change, I have the last byte of the plain text. Okay, so I'll write down the math for that. And then what I'm going to do is I'm going to do the same trick, but now I'm going to attack the second last byte. Okay, I'm going to set the last byte to 0, 2, and then I'm going to attack the second last byte until I happen to get a 0, 2 here. And then I'll reverse engineer what the value should have been that would give me a 0, 2 there. Now I have the second last byte, and I can just keep going until I decrypt the whole thing. Okay, I won't be able to go past the first block, but I can decrypt the whole tail end of the ciphertext up to the very first block, because I always have to ruin the block before in order to ruin it here. Although, actually, maybe I can go right back to the IV. Maybe I can start messing with the IV. But anyways, normally what the secrets we're looking for are usually at the end of the plain text anyways. Okay, so let me just finish the algorithm here. Okay, so let's say that we have a MAC error. I'm just going to, this is a little messy. Okay, so the unmodified ciphertext, if I use this equation here, okay, it's going to be PI is the decryption of CI XORed with CI minus 1. And what also I know is the decryption of CI XORed with my modified ciphertext. Okay, so this is my modified. Whatever I did there, it ended up in 0, 1. Okay, for the last byte. These are all just the last byte, not the last whole block. Let me, I know I should probably not be so sloppy, so let me, it's worth just writing it out exactly, explicitly, so there's no confusion. Okay. PI 15 equals the decryption under the key of CI 15 XORed CI minus 1 15. So that's just CBC decryption. That's the definition of it. Okay. Now, in my special case, what I figured out, this is the fact that I learned. The fact that I learned is if I modify this to some other value, then because I got a MAC error instead of a padding error, PI 15 should be 0, 1. All right. Now, what I want to know is I want to know this. This is the original plain text. Okay, so this is what I want to know. I don't know the key. I shouldn't be able to know anything about the plain text. But based on this fact, based on the fact that I know this, can I solve for this? Okay. All right. So what I can do is I can let me start. I'm going to start with this equation. I'm going to move the decryption over to the other side. So the decryption of K of CI 15 equals 0, 1 XOR CI minus 1 modified 15. And then I have that same, this expression here, I also have here. Okay. So let me do the same thing here. So I'll go over here. So I'll say the decryption of CI 15 equals, so I'm going to do PI 15 XORed CI minus 1 15. Okay, these two are equal. They have the same equation. Okay, so that tells me that 0, 1 XORed with my modified byte equals the plain text value that I'd like to learn, XORed with the ciphertext before I touched it. The last byte of the ciphertext before I touched it. Okay, so we can solve for PI 15. So we're going to get 0, 1. XOR, by the way, is commutative. Like you can just move it around to the other side of the equation. C prime I minus 1 15 XORed with C I minus 1 15. Okay, I've isolated the last plain text. So what visually, what is this value here? Where is it in the picture? It's not the pink thing, it's the thing that was under the pink thing, okay? The original plain text value, okay? So that's what's on the left-hand side of the equation. 0, 1 is the number that I was expecting to make it valid padding. Okay, so that's just a constant. Do I know the value 0, 1? I know it. It's not an unknown. do I know this value? So this value is what I chose here to be pink. It's what the counter was at last time when I got the MAC error. So it's at 7 or whatever, so that's that value. Okay, so I know this value. And what's this value? This value is what this byte was before I changed it. Okay, what the original value was. All right, so I know that value as well. Okay, so I have one equation, one unknown, three knowns. They're just XOR. So I just XOR these three pieces of information that I know together. And now I have the last byte of the plain text.
So what does C minus 1 mean?
It means block, let me, second last block.
Minus 1 means the second last one.
Yeah, so C means ciphertext.
Okay.
And so there's two indexing going on. The first is we have 3 blocks, and every block has 15 bytes. Yeah, so C n minus 1 just means the second last block, and then the square bracket 15 means the 15th byte of that. Does that make sense?
Yeah.
Yeah, okay. I know it's confusing, but it's just, if you're studying, you'll want to have, you'll have it written out exactly so you know exactly what byte we're talking about. Otherwise, I could sort of hand wave it away, but it might not be clear. Yeah. Okay, and then I here is any, whatever block, it can be any plain text bit that you're targeting. So it's easiest to think of it as the last one, but you can use it to target other things as well. But the padding starts at the end, so normally you have to start at the end and go all the way through. Yeah. But this is in general, like I here, you can think of I as equal to n. So I'll write that when I equals n, then we're talking about the last block. Okay, now I've decrypted the last block. Can I keep going? So I know the value here that will make this a 0, 1. So do I know a value here that will make this a 0, 2 instead? I do, right? Because it's just going to be the XOR. The XOR between the difference between 1 and 2 is the difference that will make this into a 2. Okay? So, and by the way, I just decrypted this. So I actually know what the original plain text value is, right? So I know the original plain text byte. I can figure out what's the byte that I have to XOR it by in order to give me a 2. Okay? So I can program this to be a 2 by putting the appropriate value here. And then what I'll do is I'll attack this. I'll try every possible value here until I hit a 2. And then when I hit a 2, then I'll do this. I'll see a MAC error instead of a padding error. And then I'll use this same equation and I'll figure out what the plain text byte is here, the second last one. Now that I know what the last 2 bytes are, I'll program them to be a 3 by changing the last 2 bytes here, and I'll keep going, okay? So I'm able to extract byte by byte out what the plain text is. Okay, then, so then here, so this is sort of the end. So I'm going to set this to be 0, 2. I'm going to have my counter here, so I'm going to try values here. And once XX equals 0, 2, then I'm going to see a MAC error. And then I can decrypt that byte. Okay, and then I'll keep going until I extract the whole thing. Okay. So we call this a divide and conquer attack because I'm able to attack, I'm still doing exhaustive search, right? So I'm still trying lots of values. But normally if I was going to do exhaustive search on the entire ciphertext, I would have to try like 2 to the 256 values. Now what I can do is I can just try them byte by byte. Okay? And so that ends up being a lot less work. Okay? So it's... So I'm going to do 256 times 16. That's the amount of work that I'm doing. Versus like a normal exhaustive search would be 256 to the power of 16, which is just like an enormous number that you'll never be able to tackle even with the lifetime of the universe and all the computers. Okay, questions about this attack? I see a lot of confused faces. I mean, the first time I saw it too, I didn't really believe it or understand. It's hard to like show it to you in 10 minutes and have you like walk away with it. So it's something that you might have to go home and like look over.
Whether or not it was changed. This is just to figure out if there's a mistake.
Sorry, this meaning
Like this whole algorithm.
this one here?
The one on the bottom. Yeah, the divide and conquer one.
Oh yeah, sorry, this is just describing the whole algorithm itself, yeah. Okay, look this over, think about it for a week, come back next week, ask me questions about it, and I'll go over it again if you need to. But is there any questions you have right now?
Like in the exam, what's gonna
So between now and the exam, you should bring yourself to understand this attack. This, like, honestly is like kind of a simple, it looks complicated because there's a lot of moving pieces, but in the world of attacks on cryptography, this is like a relatively simple attack.
So is this a common attack like in cryptography? Or?
No, not, so, okay, so how common is this? So this happened in TLS. I would say we call these like oracle attacks because it's leaking some information about what's happening in the plaintext. And that category, whether it's not necessarily padding versus max specifically, but just the idea that you're going to leak some little bit of information about the plaintext is very common. It's not common in the sense that these attacks are out there on every protocol. It's common that over the past 30 years, a lot of protocols have been attacked with this kind of attack. But now we know about it, and so we scrub all these attacks out. And we're very, very careful about whatever, if we throw an error message, we try to always say that, we just say it's a blanket error. We don't give any like reasons why.
And if the attacker implemented correctly, does it have a high success rate?
Sure, it works. It works. So like the only thing that stops you is you have to submit a lot of guesses to the server. So you're going to keep sending ciphertexts, and it's going to keep going error, error, error. So there is a chance that like its intrusion detection kicks in and says this traffic looks weird. Someone's asking me to decrypt the same thing over and over and over. So that's where you might get stopped. But assuming there is no network level protection, then this attack is very effective and it's very fast. And you can, these things you can do, I don't know, it takes like 10 milliseconds to do a decryption or something like that. So you can suck out like this, like you can do it on a MacBook. Like it's not like a supercomputer attack. Yeah. If it's set up right. So
question about that.
Mhm.
Now websites have like a maximum of 3 tries, but if you look at this 256 and 16 in this one, then it's about like 4100.
yeah, so 3 tries usually applies to a password, but this is not a password. This is just SSL traffic. It's like the underlying traffic itself. So there's no limit to the number of tries that you get, unless if the protocol HTTPS like gives up. If you fail too many times, it gives up. But it doesn't. There's nothing in TLS spec that does that. There could be something in the software implementation of it, but yeah. Okay, how do we fix it? So there's I don't know, there's 10 different things that you could do to fix this, because it's threading the needle of like all of these assumptions. But can you tell me one thing that we could do that could possibly fix this?
Mac.
So more specific?
Because, well,
Firstly, as you said, intrusion detection.
Okay, so we could rely on the network itself, but I want to fix the protocol itself because I don't want to make assumptions about people's networks.
Is it intrusion detection too?
Yeah, so forget about network level protections. Let's like fix the protocol itself. Then we don't have to worry about the network.
Yeah, a Mac will always tell you if there's something that was changed. Right?
Yeah, that's right.
Can we use Mac again for the full, like the equation
Okay, so we could put a Mac on the sort of the end.
for checking?
Yeah, so we could pad first and then have the Mac, and because I know the size of the Mac, then I know I can always parse out the last 40 bits or whatever the Mac size is, and then I can check the padding and all that stuff after. And then yeah. So that would work. That would fix it, because then I would never hit a padding error. Anytime I modified something, I'd hit a Mac error. Or the other thing I could do is I could put the Mac on the outside of the encryption.
Yeah, yes.
Okay, so I could encrypt first, just pad it, encrypt it, then take the ciphertext and put the Mac on the ciphertext. Then I'm never even going to start decrypting, because as soon as you modify any bit of the ciphertext, it's going to throw an error. Okay, so that's the main reason why we advocate for encrypt then Mac instead of Mac then encrypt.
So the main thing is preventing the attacker from changing the ciphertext.
So yeah, exactly. So then any ciphertext modification will fail immediately. Before you even decrypt. And so there's no chance of you leaking anything about the plain text because you don't even decrypt it.
Just encrypt, then ciphertext, and then we will do Mac with the ciphertext. So there is.
Yeah. So the way it looks is that you have your plain text byte, you encrypt it, and then you put your Mac on the end. So you fill up your message with this,
And then Mac.
and then you have a Mac on the end. And then just because we were talking about padding, there still is padding, but it's on the inside here.
So in this case, the padding error will not occur.
Yeah, so you'll never, as soon as you get a Mac error, which you will, that's the guarantee of a Mac. A Mac says you change anything, you don't know the key, you're going to get an error. Overwhelming probability. And so you're never going to decrypt. And if you never decrypt, you're never looking at the padding. Yeah. So basically, if this Mac succeeds, then this is going to be fine almost by definition. Unless if the person messed the padding up when they decrypted it. Or sorry, encrypted it. Yeah. Okay, so that's the first thing. Second thing we can do is just don't throw like different kinds of errors. Okay, so because I know the difference between a padding error and a Mac error, okay? Now sometimes though, there are systems, so there was another problem, I won't show you this attack, very, very similar. And it just threw a generic error. It didn't tell you why the error was. But what you could do is you could wait to see how long it took to figure out the error. So imagine, for example, like I'll write it this way. Okay, so don't throw different types of errors, just one error. Now, let's say you decrypt this and there's a problem with the padding byte. Okay, so say this 5 is a 4. How quickly do you learn that? You learn it pretty quickly, right? Like you looked at 2 bytes and now you know that there's an error. Okay? Let's say that the padding is fine. Now you're going to check the Mac. How long does it take to check the Mac?
The time to check the padding, this is the time.
So the padding is just you check 5 bytes, but what about the Mac itself? How many bytes do I have to look at to decide whether the Mac is correct or not?
Depends the size of the message.
Yeah, so I have to look at the entire message from start to finish. Okay, so imagine the message is, it's like I'm sending you an image or something like that because it's a website. So you're going to sit there and you're going to parse, 100 kilobytes And then at the end, you're going to say, okay, the MAC is right or wrong. Okay? So is there going to be a timing difference between a padding error and a MAC error? Yeah. Right? Okay. So you can say, I'm just going to throw one type of error, but then a padding error will basically be instant. And a MAC error, could take time. There could be a delay. And so even if you're just throwing one kind of error, I can sit there, I can measure the difference in time, and then I can guess about whether it's a padding error or a MAC error. Okay? So there's also attacks like that. And here I don't just necessarily send one. I could send 10,000 and measure the average time, and then I'll send 10,000 with the next one, and I'll notice a difference for sure between a MAC and a error. Okay? So then we get into timing errors. And so that's another kind of category of error. Okay? We call this side channel analysis because it's not in the protocol itself. The protocol, when you write it down on paper, you're not talking about how long things take. Okay, so it's outside of the protocol specification itself. But a real world attacker will use every piece of information they can gather, including the time. Okay? So what we need to do on top of doing just one error is we have to make our libraries constant time, meaning we always take the same amount of time for every task. Even if we know that we're going to fail, like we would compute the MAC anyways, even though we know it's going to fail, just so that it consumes the exact same amount of time. So there's no difference at all between the time between it. Okay. And then a third option you can do, it's kind of related to this. There's one thing that's even better than encrypt than MAC, which is you can encrypt and MAC at the same time. So there's certain modes of operations that do encryptions and MACs built into together. So we call it authenticated encryption. And so basically it MAC and encrypt together. So you're not layering the two together. And the example that we've seen in the cipher suites that we looked at, where are they? So if we go back to these things, so this GCM mode here, you'll see it's like a highly preferred method of encryption. That does that. Okay, so that's what that mode does. So it replaces CBC. So CBC is a mode of operation. And so what you do is you use AES GCM. And if you remember back in the very first class when we were reviewing 6.1.10, I said there's different levels of security for different modes of operation. And so GCM has the highest level of security, which is CCA. Whereas CBC did not. It only had CPA. And that's why we need a MAC on top of it to make the whole construction CCA. But it's also why we're hitting weird kind of mistakes and errors.
So using GCM instead of CBC will prevent the attack.
Exactly, yeah. Yeah. So that's the most preferred of all of them. Yeah. Okay, further questions? Okay, let me show you another attack, another weird attack, and then we'll move on to a different topic. Okay, so this attack is called Beast. And with Beast, there's a certain setup that we're going to use. And there's a whole bunch of attacks on SSL. Not a whole bunch, but there's probably about 4 or 5. And they all use the same setup. So this has a certain threat model and a certain thing that the adversary is trying to do. And all the other attacks, they exploit other things that are wrong with the crypto, but they do it kind of in the same setup. So you can see a bunch of variants of this attack. Okay, so again, I'm showing you this one because it also uses CBC. So we spent some time looking at CBC, so we can reuse it. Okay, so I'm going to draw you a picture of where the adversary is because it's a little bit different. And I'm going to talk a little bit about how the web works in general. Okay, so we have Alice, and Alice is on some website. Okay, and she's talking to a server. So the website was given to her from the server. And I'm going to assume the adversary is in two places. So first, I'm going to put the adversary in the middle, so they're seeing all the encrypted communication. Okay. The second thing I'm going to assume is that the adversary, for some reason, I don't know why, they're able to run a little bit of JavaScript on the website that Alice is visiting as well. It doesn't have to be JavaScript, just something like that. Okay, so assumption one, the adversary is in the middle.
The adversary puts the JavaScript in it?
Yeah, so they control the JavaScript as well. Okay, so this is, we'll call this a threat model. All right, so adversary in man in the middle position. How do they get there? BGP, hijacking, ARP spoofing, that kind of thing. Two, they're running.
Mainly they get in man in the middle because of BGP.
I'll go one at a time. Yeah, sorry. So
Mainly the adversary became man of the middle, mainly because of BGP hijacking, right?
or they're just bad, like you're connected to the wrong Wi-Fi, or they're on the same Wi-Fi
More
route.
commonly used.
Sorry?
It's more commonly used, right?
No, I don't know that it is necessarily, because it's like a real state level attack. Like you have to be a big player in order to do that attack. So it does happen. It is one route, but more common things would just be like they're between you and the server somehow. They're on the network somewhere along the path. Probably closer to your home network. Yeah, yeah.
Is it similar to cross-site scripting?
Yes, yeah. Okay, so running a script here is exactly the same as cross-site scripting. It is sort of. So cross-site scripting.
XSX?
Yeah, so SXX.
So isn't that when you put something in a form?
That's something different. No. Yeah. So
That's different? Oh.
yeah. Cross-site scripting just means that you're on site A, and the JavaScript that you're running is from website B. Yeah. Here it doesn't necessarily. You could be on the adversary's website. Like this could be the adversary's own website themselves. It's probably actually the easier scenario. Is how do you get on a website where the adversary is running a script? It could be that they did cross-site scripting into like a famous website, or it could just be that they lured you to their own website here. Yeah. Okay, so they're running a script or the whole website. Anything is sufficient. And we're not going to use all the power. You might be sweating like, oh, what's JavaScript and all that. Like it doesn't matter. Like the only thing that it can do is it can open a connection to any website it wants. Okay, so that's all I'm going to assume that JavaScript can do here. So if you come to my website, I can run some JavaScript, and the JavaScript can go to google.com, and it can go to Facebook and Instagram and TikTok. Okay, and it can open 10,000 connections to Facebook if it wanted to. Okay, so that's what I'm assuming here. So it can create outbound requests for resources. Resources are just like websites. Like give me index.html, give me, JPEG, logo.jpg or whatever. Okay. All right. Okay, the third thing I'm going to assume is that Alice is logged in some target website. Could be like social media, something like that. Okay, so then the goal of the adversary will be to hijack Alice's session. Okay, so this is the goal. Now, what does that mean? What does it mean to be logged into a website? What does it mean to hijack someone's session? So very briefly, what happens is when you go to a website and you log in, it takes the password off of you. It checks whether the password's right. Once it checks that the password's correct, it takes a secret value. The server creates a secret value for you. It gives it to your browser, and your browser keeps it. Every time your browser goes back to the website, it sends that secret value back to the website. The server looks at it and says, I recognize that secret value. It corresponds to the user Jeremy Clark. So I'm going to just log in Jeremy Clark. I'm not going to ask him for his password. I know it's him because I've seen this secret value that's associated with him. Okay? Yeah. Yeah, so sometimes they're called session IDs or a token. And the mechanism that we use for browsers to store information and repeat it back is called a cookie. So you might have heard the term cookie, but you don't have to necessarily know what that means. Okay.
Token is stored on the browser, right?
Yeah, so the browser stores it, and then it stores the website it received it from, and then it repeats it back every time you go back to that website. Yeah. Okay. All right. So here's what's going to look like, what's going to happen sort of graphically. The malicious website or the JavaScript can create basically a request. And the request is going to look like this. It's going to say, get me whatever file.jpg. Okay, and it can choose where it's going to. Okay, so it can say get that from Concordia.ca or TikTok or whatever. And the browser is going to say, okay, I have to put that on the outside of the packet because it has to route it to the proper host. Okay, so I'll put host. I'll just use Google as an example. And this is called a header because it's prepended to the file itself. Okay, so this is like the payload. And this is the header. Okay. What about the cookie? So I have a session ID. I have the secret that my browser stored for me, and I'm going to use it every time I'm about to go to Google. I'm asking for file.jpg. My browser is saying you have to tell Google who you are. Okay. So I have this token that I stored for you. You need to send that along. So where's it going to stick it? It's going to stick it in the. I'm going to write it as a cookie. It's going to put it in the header itself. All right, yeah.
Host, you mean the browser agent? Like identifying who is the agent as a host?
No, I mean like the server that you're going to itself, yeah. And then this packet will get routed to google.com. So I'm not on Google's website. I just have some JavaScript running, but JavaScript is creating the request to Google itself. So that's all I need from JavaScript. Okay, now what happens is this whole thing gets encrypted and MAC'd and all of that stuff. Okay, and what actually gets sent to google.com is the encryption of it. Okay, so what does the adversary see? If the adversary is in the middle, they see the ciphertext, the resulting ciphertext. Okay, that's what they see. Okay, all right.
This is what if it's going through HTTPS, that is, right? If it's going through HTTP, he's gonna see the plain text, right?
Sorry, I was just sort of reading. Say it again.
This is assuming it's going through HTTP.
Yeah. Sorry. Yeah. So this is an attack on HTTPS. I should have specified that. Yeah.
On TLS?
Because if it's in HTTP, then you can see the plain text.
Yeah, so it's on HTTPS uses TLS, but here it's kind of an attack on HTTPS because you're also using like the fact that there's cookie values and you know where they are and things like that. Yeah. Okay. All right. Now, okay. So what the adversary sees is the ciphertext itself. So they see the encryption of it, but the adversary also was able to choose a bunch of values here. Okay, so they know what's inside the plain text as well. They chose the host, for example. They chose the name of the file. And what they don't know, though, is the cookie value. And that's something I would like to know. If I can learn what that cookie value is, then I'll be able to log in as that user. So that's what we call session hijacking. So I copy and paste your session ID. I go to Google and I just tell them your secret. And then now Google thinks I'm you. And you just get logged in and you don't have to do anything.
But how he could hijack the session?
So if I can learn the cookie value,
For the token, right?
yeah, so if I can learn Alice's token value, her session ID, then what I'll do is I'll just go to Google, or I can go into my browser and say store Alice's session ID as my session ID.
So he just needs the cookie.
Exactly. So that cookie, think of it as a value, and it's equivalent almost to stealing someone's password. Yeah, so if you steal someone's password, you can log in as them. If you steal their cookie, you can bypass the login and just already be logged in. The only place where it's slightly weaker is that sometimes, and this is why websites do it, is let's say you want to like delete your account or you want to do like some serious change to your account. They may say, we need your password again. Yeah, so there's some times where there's like administrative things and they ask for your password to do that task. Why are they asking? They already know who you are. You're already logged in. Well, it's because they're worried that it's easier to steal a cookie than it is to steal a password.
How he gets the cookie?
So we don't know yet. Yeah, so there's no way yet. Because if this is encrypted and everything works fine, then you can send cookies encrypted. That's what the encryption's for, right? You have a secure tunnel. I'll just draw this. I'll note this as HTTPS. So I should not be able to get the cookie value out, right? Okay, so here's how I'm going to do it. Okay, so this is in like TLS, I think 1.0. You could use CBC mode. And CBC mode has this value called an IV for the first block itself. Okay, so the first block has this IV value. Okay, now here I say that the IV is supposed to be randomly chosen. Okay, the mistake that was made is that they did not choose it randomly. What they would do instead is they would just use the last ciphertext from like the last time you sent messages. So you send a bunch of messages, and whatever the last ciphertext was, the next time you're about to send more messages, you just use that value. Okay. So the IV was the last ciphertext block of previous. Record is what we call like a whole session that goes back and forth. Okay, this doesn't really matter.
Version's old, right?
Yeah, exactly. So this is an attack on an old version that's now solved.
So it's not
Yeah.
applicable right now.
I cannot, so I should have clarified this at the front. There are no attacks right now on TLS. Yeah, so I can never show you something that works today.
So no attacks on 1.3.
Yeah, or if there were, they were fixed already. So like attacks don't stick around. Like it's not like the kind of thing where someone finds an attack and then 3 years later it's still an attack. Like attacks get fixed within days, or hours.
During the break that I heard was around for like 15 years regarding Telnet on Ubuntu.
Okay.
It was like, still, apparently, if you don't get rid of telnet, it's.
I see, I see. Yeah, so maybe there's some things, but TLS is so important that things get fixed in hours or days.
Immediately.
Yeah, immediately. Yeah. So like all the attacks I'm showing you are always historic attacks. Yeah. Okay. All right. Can you see, if you're the adversary, can you see the last ciphertext of the previous record? You can. It's outside of the secure tunnel. Like the secure tunnel is the ciphertext. So that's the only property that I need to know, is I need to know that it's predictable, so I know what it is ahead of time. It doesn't really matter what it is. Even if it just always use 0 or always use 1 or something like that. The only thing I need for this attack is the adversary can know what it is ahead of time. Okay? Okay, so what the adversary is going to do is they know a bunch of stuff here, and not only do they know it, they control it. Okay? So there's more stuff in the header than just the host. There's a whole bunch of fields, and they're able to control all of those fields. Okay? And they can control how long they are. And so what the adversary is going to do is they're going to craft, well, they're going to get the browser to craft, Alice's browser, to craft a message that looks like this.
And is this in the hijacked session?
So this is not yet. No. There's no hijacking yet. Yeah. The hijacking will come if I can decrypt the cookie. So my goal right now is to decrypt the cookie, and then I can hijack. Yeah. Okay. So what the adversary will do is they'll just ask for like a certain host name or a file or any field that goes before the cookie in the header, and they can control how long it is. Okay. So what they're going to do is they're going to make it so it's exactly going to fill up almost the entire block, except for the last byte. Okay. So this will just be, I'll write it as adversary chosen. And here, what they're going to do is they're going to let the cookie start here. Okay. So the cookie, the first byte of the cookie will be in the last byte of the first block, and then the rest of the cookie will go here. And then the rest of the whole packet. And this could be many blocks long. Okay, so the point is that they're going to slide the cookie, just the first byte of the cookie, into that first block. Okay, and then if I'm able to decrypt that last byte of the first block, then I'll get the cookie value. Then I'm going to slide the cookie over. So I'm going to make this a little shorter. Whatever I'm putting here, I'll make it 1 byte shorter. And then I'll slide the cookie over, and I'll have the second byte. And then I'm going to slide it over byte by byte. Okay? And my goal here is to decrypt just this last byte. So I'm not trying to get the whole cookie at once. I'm just going to try and get the last byte of this first block itself. Okay? So this is P1. This is P2. Onward. Okay. Now let's look at encryption. Okay, so I have the plain text. What's the first thing I do with it? So I XOR it with the initialization vector.
Yeah.
Do I know what the initialization vector is?
Yes.
I do. So I know ahead of time. If I wanted to change the initialization vector, I could change it, right?
Yes.
Okay. And if I change it, what happens? So let me just think for a second. I'm wondering if I need the decryption algorithm. Yeah, sorry, I should copy the decryption. let's say I change the last byte of the initialization vector. Okay, I know what it's going to be, so I can change it to something else. What's going to happen?
The last byte, the plain text will change.
Okay, so the person's going to go, they're going to decrypt it, and the only change that's going to happen is here. Okay, nothing's going to change. The rest of the plain text will be the same. The rest of the rest of the plain text will be the change. Okay. Sorry, I'm just trying to review this. Actually, I'll tell you what. Let's take a break, 10 minutes, and I'm just going to recall exactly how this works. Okay, so I worked out the details. I had to remind myself. Okay, so what we need actually is just the encryption algorithm here. All right, so this is what I'm going to do. I'm going to choose the first bytes of the plain text with the JavaScript. I'll just program it to something of my choice. And then what I'll do is I'll have the browser drop the first byte of the cookie here. I can't see it. I can just see the resulting encryption of it. Okay? All right. So what I'm going to do is I'm going to just let the browser encrypt it. I'll get the ciphertext block. Okay? So the ciphertext block will be this weird plain text where I chose the first bytes and I don't know the last byte. This is the cookie value that I'm trying to recover. So this is my plain text. It's going to get XORed with the initialization vector. We'll call it IV1. And then it's going to get encrypted. So you'll get the ciphertext out here. So that's the ciphertext. And what will go across the wire? What will I see? I'll see the ciphertext value. And you always send the IV as well. So the IV is not a secret. It's just a kind of like a salt value. You create it. And the person who decrypts it, they need to know what the IV is in order to decrypt it.
Who can see the IV?
Everyone. So it's clear text. Yeah. Otherwise, we call it a key.
That means it's a salt.
Yeah. So it's like a salt. Think of it. Yeah.
But the IV that you use here is the ciphertext of the last.
Yeah. So I actually knew what it was ahead of time. I'm not using that fact yet. I will use that fact, but right now I'm not using that fact. Okay. All right. So I just encrypt. I encrypt it. I let it do its thing. I see the ciphertext. So normally the IVs are, unpredictable. So that would be random. And you'll see why actually they need to be unpredictable. Yeah. What does unpredictable mean? It means that you don't know what it is until you're ready to decrypt. Like it will become public, but it's like I already am holding the plain text in my hand that I want to decrypt. Now I'm going to figure out what the IV is. I don't know the IV before I craft my plain text. If I know the IV before I craft my plain text, I could change my plain text using the IV value. Okay? So that's what this attack is. Okay? So what I'm going to do is I'm going to then send out a second request to the same website. But this time I'm going to craft it a little different. So I'm still choosing the first block. Whatever I put here, I'm going to put the exact same thing here. I don't know what the cookie value is here. I'm going to put a guess. So I'm going to try 0, 0. Maybe it's 0, 0. If it's not right, then I'll try 0, 1. I'll try 0, 2. But for now, I'm just going to try 0, 0.
You know how many bytes it's going to be?
Yeah, so I know that remember the cookie is I do know how long it is, and it's longer than a single byte, but I've slid just the first byte into the first block. Yeah, and then I'll attack the rest of the bytes later. Okay?
This is how the adversary is doing.
Yeah, this is how the adversary is doing it. And the idea of being able to do it byte by byte, that's the divide and conquer. So it's the same as before, where wherever I had it. So it's going to be like 256 times 16 rather than 2 to the 56 to the 16. Yeah. So I write in a guess, 0, 0. Okay. Then what I'm going to do is I'm going to XOR the initialization vector that was used the last time. Okay. and I'm going to XOR the initialization vector that's about to be used. Okay? I know what the initialization vector is that is about to be used, right? Because it's predictable. Okay? Then I pass, so this is the plain text. So the plain text is this value, XOR this value, XOR this value. Okay, so these three things, I XOR them together. I hand it to the browser and say to encrypt it. Okay, so the browser says, okay, there's that plain text value. I'm going to XOR it with the initialization vector. Okay, so I'm going to XOR it with IV2. What happens? Okay, but before just, so that's right, that's where we're ultimately going. But just here, when I just apply this XOR to this plain text, do you notice anything happening? So I have IV2 here. I'm XORing it with this value. What's this value again? Okay. It's the thing I chose, XORed with IV1, XORed with IV2.
Yes. So you would actually see, like, to give you an idea of what the IV1 is, even though you don't really know what IV1 is.
So I know IV1 because I saw it. It was the thing that was encrypted the first time. Yeah. So I stole IV1 from the last time I encrypted. Yeah. And IV2, I didn't know what I shouldn't know what it is until the browser should invent it. I should have to hand the plain text to the browser, then the browser chooses IV2. The flaw here is that I know ahead of time what it is. It's like the last block of this or something like that. It doesn't really matter why I know it, I know it. Yeah. So I'm able to XOR it into the thing that I'm asking the browser to encrypt. Okay. Now my question is, I'm XORing by IV2 here, and then the browser is going to take it and XOR it by IV2 again. What happens if you XOR something by the same value twice? It cancels out. Okay, it gives you 0. Okay, so something like if you have some value X and you XOR it by A and then you XOR it by A again, it's like you didn't XOR it by A at all. They just cancel each other out. Okay, so that's the key here. So what will happen is that this will cancel out with this. And what it will end up encrypting is this. Okay? So the same thing as here with your guess here, XORed with IV1. This is exactly the same as what was encrypted here.
That means the cookies you can now guess.
Okay, so what does it mean? Well, now what I'm going to do is I'm going to sit on the wire, and when C2 goes by, I'm going to say, hey, is it the same value or not? Okay? Is C1 equals C2? If they're the same value, what does that tell me about the guess?
The cookies.
It's the same value as the cookie, yeah? And if my guess was wrong, then the C's will be different, okay? Then I'll just do it again, right? So then I'll increment my guess. I'll make it a 1 instead of a 0. And then I'll do it again, but now I'll XOR in IV3. Sorry? Yeah, and then I'll do an exhaustive search. Yeah. And eventually my guess will be right. And then once it's right, then what I'll do is I'll slide the cookie over. I'll slide the next byte of the cookie over, and then I'll do the same process, and then I'll extract it byte by byte. Okay? So what's the problem here? The problem here is I can predict what the cipher, or actually the problem here, it actually goes back to like the definition of CPA security. If I ask for the encryption of the exact same thing, I get the exact same output. Okay? We don't like that encryption. Okay? We don't want the encryption of the same thing to result in the same ciphertext. We want a different ciphertext. Okay? So the principle that's being violated is same plain text leads to the same ciphertext. Okay, so it's not CPA secure. How do we fix it? Well, that's actually what the role of the IV is. Okay, the IV is meant to fix that problem. Okay? Why is it not working? It's not working because I'm neutralizing the IV. I know ahead of time what it's going to be. I just toss it into the plain text so that when the IV gets applied to my plain text, it cancels out. Okay? So because I'm able to predict the IV, I'm able to cancel out the IV. And because I'm able to cancel it out, now it's as if there is no IV. So I've reduced something that should be CPA secure to something that's not CPA secure. Okay? So by having a predictable IV, I can cancel okay. And then the idea here is just that I can steal the cookie byte by byte. And then once I've stolen it, I can do the session hijacking. Okay. And the reason, now does this work for any data? Can I just use this attack on anything, like on a password or something like that? The reason I'm able to do this is because of the whole setup, the browser is putting the cookie into the plain text. Okay? If I was going to attack your credit card number, I can't get the browser to put your credit card number into traffic, right? I can't get it to put your password into traffic. I can't just say, go get this file, and then your browser's going to go get your credit card number and stick it in. Okay? But with cookies, that's how cookies work. The job of the browser is to go grab that value. It is a secret, and it's going to stick it in. Okay? So this overall setup of an adversary in the middle looking at stuff and having some control over what's encrypted, that's what the JavaScript is getting them. They get to choose the values that are going to get encrypted. And then because they're in the middle, they can see what the result of that is. So they choose the value ahead of time. It gets encrypted. Then they see what the value is that's encrypted because they're sitting on the wire. Okay? Then they're able to put those two pieces of information together and try and break. Okay? If it's CPA secure or CCA secure, it shouldn't matter that the adversary is in this position because the whole game of CPA security was the adversary can encrypt whatever they want. Right? They're allowed to encrypt whatever they want. They're allowed to see what the encryption of that is. It still doesn't let them break anything. Okay? But here we have basically like a CPA game where the adversary is able to ask for the encryption of anything they want. They're able to see the result, but we're able to leverage that into breaking the protocol because of the fact that the IV was predictable. Okay, questions on that? Okay, so again, hopefully you kind of get the intuition, or at least you know enough to like try and review it. These attacks are kind of complicated, but anyways, unfortunately, there's no easy attacks on protocols. Protocols are complicated. The attacks are complicated as a consequence of that. But in this course, you should be able to know, you should be able to follow like attacks and understand why they're happening and how to fix them.
Is it like a hacker that they discovered was doing this, or is it like some researchers discovered that there was a vulnerability?
So Beast was some researchers. They discovered it. I think they gave a talk at DEF CON or Black Hat or something like that. And yeah, I think they disclosed it before. So then I think everyone fixed it before they revealed the details, if I recall correctly. That's a standard thing that happens, but I don't remember in this case specifically. I just remember they like had a whole website with the attack and they had a logo, and then it became this thing that like if you find a new attack, you have to give it a cool name and have like a logo for your attack.
So this is proving that it's not CPA secure, right?
Correct, yeah.
Okay.
So the bottom line was that because the initialization vector was predictable, CBC mode lost its CPA-ness. And because it wasn't CPA secure, if you ask for the encryption of the exact same thing, you'll get the exact same response.
And if it's CCA, so it'll be secure?
Yeah, if it's CCA, then CCA subsumes CPA. So you don't need, the CCA-ness isn't adding anything to prevent this attack. What you need for this attack is the encryption of the same thing results in something different.
Yeah.
You get that when you go to the CPA level, and then if you go to the CCA level, it adds other security properties on top. But there's no encryption that's CCA secure that's not CPA secure. It's strictly higher.
So how to fix this type of attack?
Yeah, so what you need to do is just not make so choose the IV after the plain text. Yeah, so fix. So that was fixed. That was the fix that was made. And then as a result of that fix, CBC mode is still used. So you'll still see it. I think there were, yeah, so you can see like CBC here. It's considered weak, but anyways, it's still an acceptable parameter.
And like you said, the downgrading is impossible, like, because of the MAC that they put.
Correct. Yeah. Okay, so in summary, that's a good thing to come back to. So we saw 4 attacks, right? We saw the downgrade attack, we saw Beast, we saw the padding oracle attack, and we saw one other attack. What was it? Just a basic replay attack. There's a bunch more. Okay, so I could keep going for 3 lectures and show you Poodle and like there's RC4 biases and things like that. But I wanted to give you a flavor of sort of what the attacks look like. All the attacks that we saw are like pretty generalizable to other protocols. So replays are something that you always have to protect against, usually always with nonces. Downgrade, you always have to think about when you have multiple versions or different things that can be configured. The padding oracle attack is similar to other kinds of attacks. So if you go and look at other attacks on TLS, you'll see like that sort of side channel analysis, the idea of like just leaking a single bit about what the plaintext is enough to like extract plaintext. So you'll see that kind of theme in a lot of different attacks. And then this attack as well, this is like a web-specific attack, but for HTTPS, there are a bunch that have the same assumption where you're able to craft ciphertext and you're able to observe them when they go across the wire. Okay, questions about this?
I have a question on
Yeah.
the last attack. What do you mean by the JavaScript?
So JavaScript is just something that when you download a website, it's code that's running in the website that you're looking at. Yeah?
Like front end with HTML.
No, I mean by running the script on the
Client
website
side?
or the whole site.
Yeah, so it's client-side scripting.
Okay.
Yeah. So it just means that when I download the website, it comes down with some code. And now my browser starts running that code. And that code can do anything. Like it can't do anything, but it can do a lot of things. So it can connect to a server and get instructions.
So the adversary takes that code?
Yeah, so the adversary put that code in the website, or you just went to the adversary's website.
Okay.
Yeah? And so once they have that code, the code could call the adversary and say, what do you want me to do? Then the adversary can tell it, go load Google 10,000 times with these values, and then they will do it, kind of thing. So JavaScript can open connections to anywhere. It can receive back data, and then it can behave based on what it's receiving. Or it could all be programmed into the JavaScript when you initially download it. Yeah?
So we inject the code.
Yeah, so the code's running on the website. Yeah. So injection means that it's like someone else's and you were able to put it in. But even with Beast, it could be like the more normal scenario would be I would just like send you a text message like, I don't know, check your taxes or like there's a problem with your pay bill. You go to the website. Now you're on an adversarially controlled website and it can start running this JavaScript in the background and doing this kind of attack.
Okay.
Yeah. Now this is also the kind of thing that intrusion detection would probably take care of. So because I have to do an exhaustive search of all my guesses, either an IDS here or an IDS, say at Google, like they'll notice all this traffic and not be happy about it, they'll probably cut me off. Okay, so there is some limited, like, real world viability, but we absolutely do not want a protocol that has flaws in it and then just have to rely on network security to save us, right? We want the protocols themselves to be secure. Okay. All right, I'm going to move on. So I'm going to show you one other thing related to HTTPS. Before I do, I just want to remind you. So what's HTTPS? So we have HTTP. So this is like web stuff. Then we're going to feed it into TLS. And this is going to give us encryption.
So it becomes HTTPS.
Yeah. And then together, we call that HTTPS. So now I have my encrypted HTTP packets. What do I do next? What's the next like kind of protocol that I'll use?
TCP?
Okay, so I'm going to use TCP. So I'm going to drop it on the network.
Or UDP?
And then IP will route it to where it needs to go. Okay, now someone was saying or UDP. Can you do HTTPS over UDP?
Actually,
No.
Yes, we can.
Yes, you can. Yes, you can.
So some people say yes, some people say no. Convince me one way or another.
the only difference is that you're waiting to acknowledge that you received the packet, and then you send an acknowledgement back. And
So that is one big difference between TCP. I think I have it here.
and then UDP, you don't send that.
So we do this handshake at the start of TCP. So with UDP, we get to skip this handshake. So it would be faster to do it over UDP. Okay, but is there anything else that TCP is doing for us?
More secure,
Okay, in what sense?
because there's acknowledgement and synchronization between two.
Okay, so the three-way handshake does something. I'm going to show you what that something is in a second. But yeah, so there's that. But does TCP also add anything else besides the three-way? Is that the only difference between TCP and UDP? So yeah.
UDP is faster than TCP.
So it's faster only because you skip this step, or mainly because you skip this step. Yeah. What UDP does is it also has no like TCP has a bunch of like checksums and things like that, and it has packet numbers, and so like you get the packets, you get them in order. If you're missing something, you know you're missing it. If there's a mistake in it, you can recover from that mistake. Okay. So there's a bunch of like control over it, and UDP is just you send the packets, and the person receives them maybe out of order and just does what they want with them. And if something gets dropped or corrupted, then they drop it or they show it to you corrupted, you know. So UDP, you can think of it as like you're streaming a movie, right? And maybe there's some noise on the network or some problems, then the video kind of skips or jumps or there's like static or whatever. But you don't ask for those packets, like you just move on. You show what you can of what you know about the video, and then you move on to the next frame. And if packets got messed up, it gets choppy for a while, and then you keep going.
But it doesn't mean that the HTTPS is not working, right? Because I think about YouTube. Does YouTube work like that?
So yeah, that's a good question. So I'll tell you the answer in a second. Okay, so this stack is how HTTPS worked, or how HTTP itself worked for the first kind of like two versions of it. So we call it 1.1 and 1.2. Sorry, just two. I don't know why the numbering is weird. Okay. And now what we have is we have a new version of HTTP, version 3. And for version 3, what we're going to do is we're actually going to run it over UDP instead. But because UDP isn't as strong as TCP, we have to do things a little different. Okay? So HTTP3, we're going to make a couple changes. Our goal basically is to make it faster, so I want a faster handshake. there's a couple other features that I'll show you that are just like cool things that were added that I guess you could maybe like try and find a way to add something similar, but we just added it. And then the problem with this is when we switch from TCP to UDP, we get rid of the three-way handshake. So we have to think through the consequences of that. Does that matter? Yeah, is there some sort of attack that's now possible that wasn't possible before? And we also lose all our like version control, or all our like control over, you know, packet ordering and stuff like that. Do we care about that stuff? If we do, we have to add it in. But we could add it into like this layer here. Okay, so this stack we call QUIC. And so QUIC is basically just HTTP plus TLS over UDP. It uses the same handshake, but it does things at a different stage. Basically, the handshake completes a lot faster. Okay. So let's go through QUIC, and I'm just going to highlight some of the differences. I won't go through the whole protocol, but I'll show you some of the improvements that were made. Okay. I'll make it more of a ladder diagram because it'll be a little easier. Okay, what Alice does first is what we want to do in QUIC, this is like one of the features, is we like the very first message that's being sent to be encrypted. Okay, we don't want to do a handshake in plain text and then switch over to encryption. But we have a problem, which is if Alice has never talked to the server, they can't possibly share a key that's in common. Okay, so they don't have that key yet. Until they get the certificate from the server, they don't know what the server's key is. And until they do, like, say, a Diffie-Hellman handshake or something like that, they're not going to have like a symmetric key encryption. Okay, so it's basically impossible to do an encryption on the first step, except for you can do a kind of weird encryption where you encrypt it and you send the key. Okay, so you just pick a key and you send it along with the first ciphertext. Anyone in the middle could decrypt it trivially. Okay, they can just look at it. The key's sitting there. It's in ciphertext. They could decrypt it. So why would we even bother doing that level of encryption? And so the answer is that it's not so much a security thing. It's more about like when you buy, like, say, a router and you put it in your home, your router's like, it's not just like routing traffic, it's actually looking at it. And it's trying to make like decisions about like things. And it's like doing some inspection of it. And generally now we've come to the point that we don't like that. Okay, we don't like routers because they don't help. And sometimes we change protocols or we want to improve it. And now the routers are like barfing on the like thing that's going across because it's not what they're expecting and things like that. Okay, so the reason that we normally do this initial encryption is just to stop or try to prevent or throw some friction at these routers who are doing packet inspection. It also means that if you're in the middle, you have to be a little more clever. You can't just look. You have to be able to take the key and there's another salt value and you have to know the version and you're going to have to pull that in and then you're going to have to decrypt on the fly. So you're going to have to run a decryption algorithm on the fly and look at it. So it's going to make it a lot harder to be in the middle in order to just sort of passively look at traffic and try and figure out what's going on. Okay, it's going to put more effort on the middle. Okay, so this is one of the first things that QUIC does that is not part of HTTPS. I'll call it initial encryption. Okay, so what Alice does is she picks a key at random, and she's going to do this for every session. So every server, she's going to pick a different key. There's a name for it. It's called DCID. I don't know if I wrote down what that means. I can't remember. Thank you. Destination, some people study QUIC here. Yeah. Destination connection, right?
Connection.
Yeah. Okay. And so what this is it's just like a random key. I'll put key in quotes because it's not a secret key. And, okay. And then what Alice is going to do is she's going to take DCID. She's going to XOR it with a salt value. And the salt value is going to be from QUIC itself. And they're just going to publish different versions and things like that have different salt values. But basically, once you decide what version you're using, there's just one value that's always used. Okay, so it's going to be in the QUIC standards. So again, not a secret. But over time, as new standards come out, then the salt values will evolve. And so any routers that were created at a certain point in time and no one's updated the firmware of those routers, they can't possibly know about what the salt values are in the future. Okay, so a router that's made today might, if I make it smart enough, I could make it decrypt, break this initial encryption for all versions of QUIC up to today. But once I ship it to the customer, I can't change it anymore. The customer has to come back and ask for new firmware or something like that. Okay, so it's going to be hard for me to continually decrypt this thing. Okay, and once I have these two values, I'll run it through KDF, key derivation function. Sorry, we were calling it PRG before. I'll call it PRG. And then I have my initial secret. And I'm going to, this is slightly abusive, but I'm going to try and make it look more TLS-like. So we'll call this an extractor. So I'll run it through an extractor. I'll get the initial secret. Then I'll take my initial secret. I'll run it through a PRG. And then I can blow it up to as many keys as I want. So I'll get all my standard keys that I need. MAC keys, encryption keys, all that type of stuff. Okay, what I send across the wire is I send just the DC ID, and then there'll be some other stuff that goes along with it, okay? And then the server is going to do the exact same thing. So they're going to take the DC ID, they're going to XOR it with the salt that they got from the spec. Extract it, get the master secret, expand the master secret out into as many keys as they need. So it might be one encryption key in one direction, one encryption key in the other direction, one MAC key in one direction, one MAC key in the other direction. Okay, so now we have both parties. They have the same ciphertext, and then what we can do is we can just encrypt right away. Normally here we're using authenticated encryption, CCA, in QUIC. So we like kind of got rid of like CBC mode and all that stuff, and then we just send basically our first message. I'll just write payload here. How it looks, I'll show you in a second. Okay, and so the main thing that I'm trying to solve here is if there's an adversary in the middle, and I'm going to call it a middle box. So a middle box is kind of like a router or something like that, and it's doing packet inspection. I'd like it for it not to do packet inspection, okay? Maybe for privacy, also just like I don't really trust all these home routers, and sometimes they make weird optimization decisions and things like that. And I want to be able to make changes in the future and not have to worry about whether middle boxes are going to like it or not. So that's the main motivation. Okay, so that's the first thing that we try, okay? Sorry, the first thing that we change. Okay, questions about this? Okay. Second thing I want to talk about is I want to talk about the switch from TCP to UDP. And in particular, I want to talk about dropping the three-way handshake. Okay. Tell me one good thing about dropping this three-way handshake. Faster, okay, speed, efficiency. Okay, I don't have to hi, back, hi. I received your hi back, and then now we can start doing the handshake, okay? Can you think of any reason why this might be bad?
Authentication, like
It's not reliable.
Okay, in what sense?
Loss of packets.
Okay, so it could be that packets will get lost. Anything else?
Everybody, like, there's no, let's say, like every, for, in the case of UDP, it's more or less like you're kind of broadcasting the message to everyone, not caring who sees what or who hears it. So I think that'll probably be confidentiality good. So I think in that case, you are giving up that, right?
Possibly, but we are going to ultimately wrap it in encryption, so I'm not so concerned about that. So only the three-way handshake. What's the purpose of the three-way handshake? Why do we even do it?
Because you want to acknowledge that you received the packet.
Okay, why do we care?
Because
I mean, eventually, with this, if I send stuff to the server and they don't respond, they're not going to respond. Like, it doesn't matter if it's on the handshake or if it's on the first packet.
It's like they, both parties know each other, like the server and the client both know each other. Like one is sending the packet and another just acknowledging means it knows that the packet is coming from which destination.
Okay, and what does that tell you?
So like you can send packets like you can slot it. Like if they don't acknowledge that it's from you, you're gonna like keep sending them. I guess.
Okay, so there's something maybe with like a DOS kind of attack, like a flooding attack, right? Okay, and there's something with like knowing, like sort of some sort of double authentication.
Double authentication, yeah.
I'm not sure, but the UDP stays open, but the TCP closed after like the transferring packets.
Right. Yeah, so that also, like, that could be something we'll talk about later, but here just for the three-way handshake at the start. Yeah.
UDP has no integrity.
No integrity. Yeah, so TCP doesn't either, well, it does, but like it, not against an adversary. So if there's random disturbances in the packet, TCP will fix them. It will detect them. But if an adversary goes in, they can change it, but then they can also change the error correcting code so that they reflect the right value as well. So yeah, so there is less integrity. But right now, I'm not even worried about TCP versus UDP beyond the three-way handshake. I just want to understand, like, why do we say hi back? I heard your hi in the first place.
it's because in TCP, sorry, go ahead.
So 1-1 relationship means,
Because
yeah.
from what you said before, TCP, you have to, when you send the packet, it has to acknowledge that it received the packet. If you didn't acknowledge it, then it sends the same pack. If you don't acknowledge it, it doesn't send the next packet, right?
Yeah.
So in UDP, doesn't matter if it doesn't.
But why do we care about that? So you're right. This
You
is
wanted to- because you want to receive like the whole bit string that you're sending when you're sending it TCP. You don't want to, if any packet gets lost, then you have to resend that packet. That's sort of, but I don't know why it does it. That's just the way the program.
okay. I understand, but I don't see why the handshake helps necessarily. Yeah.
It's like keep them in sync, I think.
If say again.
To keep them in sync.
Synchronization.
Yeah. So the handshake, sort of. Yeah. You're hovering around the right answer.
To get public
They're supposed
keys
to
and
message
certificate
everybody.
signature.
Okay. Public keys will come later. Yeah.
Message rewind.
So that's another feature that we'll talk about later, but that's not for the three-way handshake.
It's like screaming. We are talking right now, but let's say if I'm in another room, UDP would be like that. You're basically screaming it, but you don't know if the other person is listening or not.
Okay,
But-
but I'll find out very quickly.
TCP right now, we are talking to each other while looking at each other. It would not mean like if I'm speaking, you are listening to me.
So,
Okay, so that's close. Yeah.
are you referring to availability?
No, not availability. Yeah.
I think a three-way handshake is because we try to establish a connection and we see the server like the other side is up, that the server can respond to our message before sending the packet.
Okay, so it does do that, but even in UDP, I'll ask for something, and if I don't hear back, then I'll quickly know whether the server is responding or not.
Are you talking about something related to how Nmap works?
No.
Okay, because I know with that type of Nmap attack, they send packet and stuff like that.
Where did you mention something about SYN checking?
Yeah.
Is it with this?
So it's related to the handshake, but not why you do the handshake. Yeah. So that this is the handshake itself. SYN ACK. Okay, so everybody is like really concerned about being Alice and connecting to a server. And what do I know about the server? Okay.
The server has like a CPU memory.
Yeah, so it's true. Like it is a short set of messages. We'll come back to that as well. But in UDP, you could also just send a quick, like, okay, I'm here, I'm ready to do UDP. Yeah. Okay, so everyone's concerned about Alice knowing something about the server. Okay, I'll tell you in TCP, UDP, three-way handshake or not, you're going to find out about the server anyways, right? You're going to ask for something and you're either going to get an answer or not. Okay. The three-way handshake is about the opposite. Okay, it's about the mutual authentication. It's about the server knowing something about the person. Okay, we do the three-way handshake because the server wants to figure out something about Alice.
What's the thing?
So what is the thing? Okay,
The history is the
sort of. I'll give you the answer. What the server wants to know is, Alice, were you really the one that sent me this request? Okay. Why would the server even have to ask that question? The answer is that I can create a request to Google and I can put your IP address as the sender. So Google receives it and they say, okay, this person asked for something, and then they send it back to that person, but the person never asked for it. Okay, so we call that IP spoofing, and the three-way handshake breaks the IP spoofing. What happens is I spoof an IP address, I send it to the server, and then the server sends the response back to the IP that I listed, and that IP is like, I don't know what you're talking. Why are you saying hi to me? I never said hi to you. And then it just drops it. Okay, so the three-way handshake establishes that the client is the one that's actually asking for it. It's not like some sort of spoofing attack.
This is authentication.
So it doesn't authenticate.
Two-way authentication. Server is
Yeah.
also confirming that it's a real client.
Sort of, yeah. It's the client that asks for that
for
information.
messages,
Yeah. So authentication I think of as stronger, like that's more of a cryptographic thing, but it's that idea. Yeah.
So we do it to confirm the identity of the client, right?
Exactly. We confirm.
Prevent IP spoofing.
Yeah, exactly. Yeah. So I'll just write as it allows IP spoofing. Okay, and then let me draw a picture so it's really clear. So here's the victim. Here's the server. Here's the adversary. I should draw them up top. So the adversary says SYN, and the IP address they use is Alice's IP here. I'll put IP star. The server says, okay, I'll send an ACK back to IP star. And then victim says, I'm not expecting an ACK. And so I'll just drop it.
So how would this be malicious?
Exactly. So big deal. So you can spoof IP addresses. We're going to get rid of the three-way handshake. Now this isn't going to work, right? The adversary can send it, and the server's like, okay, you want to talk UDP to me? Sure, here I go. And it will start sending whatever you ask for to it. Why do we care? What possible damage could we do with IP spoofing? Okay, so tell me how.
So we can keep sending message that with the victim IP that we want to connect, and then the server gonna respond to the.
Okay, so I go to YouTube and I say, give me video number, lecture 4 of INSE 6120. And I say, give me the lecture, give me the lecture, give me the lecture, give me the lecture as fast as I can. What's going to happen is it's going to start sending the lecture, the entire lecture, to the victim as fast as I'm asking for it. How much data do I need to ask for the lecture? Just a little bit. How big is the movie file of the lecture? It's big, right? So I'm going to spam Google or YouTube as fast as I can, and it's going to send packets that are bigger than what I requested. Okay, so we call this an amplification attack. So I sent a small request and I get a big response. And this will work in UDP. It will not work. Why doesn't it work in TCP? Yeah, so the ACK is a small message. Basically, the ACK is the same size as the SYN. So it's basically one-to-one. So I can SYN, and it will ACK, but I might as well just SYN, or ping directly to the victim. It's not actually amplifying anything. Yeah. So that's why a three-way handshake. And then because it gets dropped before the server sends real data, then there's no amplification that's possible. Yeah. But once we switch to UDP, on the very first message, I can say, give me something, and then it's going to start giving me stuff that's going to be a lot bigger. Yeah? Okay, so amplification.
It's sort of like it's going to overburden the server?
Yeah, it's going to overburden the victim, but what I'm assuming here is that the server's bandwidth is bigger than mine. So I'm sending packets like at a certain rate to the server. It's sending packets that are bigger to the victim, and I'm assuming that the server's bandwidth is bigger than both mine and the victim. So I'm able to amplify it. The server can keep up, and then the victim's going to get dropped offline. But if the server cannot keep up, what can I do? I can find 5 or 10 servers or 100 servers, and I can just send 1/10 of my traffic to each of them. But then all of them are going to point back to the same victim. Okay? And then I can get a botnet, and I can have my botnet do the same thing, right? So all of us are hammering the server, and the server's sending all that traffic to the victim. Yeah. So let me draw that out as an amplification.
It's taken care of in the code, right? But
Correct.
still we can DOS.
Yeah, that's where I'm going. I will. Yeah. So we're going to have to do something in QUIC to prevent this. But this is the motivation for why we need to do it. Okay, so I send a request, and they're like really small requests. And then what the server will do is it will send a response. But the response for each request is bigger than the request. And it's going to hammer Alice with this. Okay, so we call it amplification. And this has to be UDP. If TCP size of SYN and ACK are similar. Okay, so what are some things in the middle that would allow us to blow up small requests into big responses? So there's a bunch historically that have been used. So even before QUIC, there's things like, there's a time protocol, NTP, where you could go to any server and say, what time is it? And it would tell you what time it is. And you could say, give me like the last 10 people that connected to you. And then it would give you the last 10. And the last 10, that data packet's a lot bigger than just give me the last 10 people that connected to you. DNS, you can go, now there's DNS sec. It runs over UDP. So you can say give me the IP for Google, give me the IP for Google, give me the IP for Google. But now it's not just like Google's IP is this, it's Google's IP is this, and here's a certificate, and there's a digital signature on it, and then that's signed by a CA, and here's the CA certificate. And so you end up with a whole bunch of data, okay? And now, potentially with QUIC, right, it's going to be the same thing, because the first step of the handshake is I'm going to say, I want to talk HTTPS, and the server is going to say, here's my certificate. And the certificate is going to be bigger than me saying, I want to talk HTTPS to you, okay? And so we're going to get amplification, the potential for amplification here as a result, okay?
So what that does is going to take the victim off the internet?
Yeah, exactly, yeah, it's a denial of service attack on the victim, yeah. And then we can use botnets here. I can go run a botnet for an hour. So I can have people all over the world doing the same thing. And then I can also like diversify. I can like distribute it across multiple servers. But always have it pointing at the same victim. Yeah. So it's sort of a distributed denial of service amplification kind of attack. And this is how denial of service is done nowadays. It's with amplification. Okay. So in QUIC, what I want to do is I want to fix amplification. How can I fix it?
Can you fix the length?
Okay, so first thing is that QUIC says it has as a policy that the server will track how many bytes it has received from the client. Okay, so the client says, hi, I want to talk HTTPS, here's my DC ID, blah, 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 blah. Okay, that is a certain number of kilobytes. Server will remember that. And the protocol says you can never send whatever you want to tell to the client. You can only send 3 times what you received, up to 3 times, okay? If you want to send more, if you're in the middle of your certificate and it gets clipped off because you run out of bytes, then you just tell the client, sorry, I can't send more, error, like I don't have enough budget to send it, okay? Then what the client will do is they'll just send you garbage that's a certain length just to sort of free you up so that you can send more of your certificate down to the client, okay? So it will just send you random padding or whatever. But what it's doing is it's proving that A, it is the right recipient. Like it was the one that asked for the connection. It's not an IP spoofing thing in the middle, okay? And then you're always honoring this like 3x thing, okay? So server will track how many bytes it's received from the client, and then it can only send back 3x until the handshake is complete. And here by handshake, I don't mean the 3-way TCP handshake, I mean the TLS handshake, so I should specify that. Here we're only going to use Diffie-Hellman, so we're only going to use TLS 3.0, or sorry, TLS 1.3. So I'll just write it as until Diffie-Hellman exchange is done. Yeah, so once both sides are authenticated, they both have a key, then you can go, okay? Another thing that QUIC can do is they can do a retry. And so with the retry method, basically what will happen is Alice will send the DCI and the payload, and the server will say, wait a minute, I don't want to talk to you yet. I'm going to send you a random challenge, and I want you to repeat that random challenge back to me. And if you repeat it back to me, then I'll talk to you. Okay?
That means the verification, kind of.
Yeah, so it basically is a three-way handshake at this point, right? Client says something hi to them. They acknowledge it by sending a message back, and then you acknowledge that you received it and you're willing to communicate by repeating the message back, okay? So it's a challenge response, yeah. The fact is that it is a three-way handshake, and so it ends up being TCP anyways. So if you really don't like that this is running over UDP and you want to do the three-way handshake anyway, you can use this retry as a sort of way of kind of doing a three-way handshake kind of thing. Yeah. Yeah. So the server sends challenge, and then the client, or I'll put user echoes back the challenge. And so this is basically equivalent to a three-way handshake. This is 100% optional, okay? So you don't have to do this. Do servers do it in real life? No, like almost no one does it, okay? You might do it if you think for some reason that it might be like a DOS attack, like maybe you've seen them recently, or it's going to a weird IP address or something like that. Like usually it's like more of a networking level decision kicks in. You're like, I don't like this connection for some reason. It feels weird to me. So I'm going to do this retry mechanism. But generally we don't do it.
When server receives like more than certain number of requests from one IP address, it sends a retry packet that okay, you like verify yourself that.
Okay, yeah, great. So what?
It's like 64 or 128.
Okay, yeah. So what's a weird pattern that looks like it might be an amplification? One is I'm receiving a lot of sessions from the same user, yeah, or requests from the same user. Then I'll kick in and do a retry. Okay, and then the final thing is, can we just skip this whole thing? Okay, and so the answer is, I can't if I've never talked to you before. Okay, but let's say I have talked to you before. You verified who I am, and we were just talking an hour ago, and now I'm coming back to you. What can happen is the server can give you a secret. You remember the secret, and then you come back later and you say, hey, it's me again. Here's the secret that you gave me last time. And now the server's like, okay, I know who you are, and so I'm okay. We can skip this whole like thing, and we can even skip the whole handshake if we want. We can just go, we can use that secret directly in order to derive keys right away.
Similar like cookies. Cookies is in the browser, but it is in the server now. Cookies also.
Yeah, it is similar, yeah.
If you come back, then it's not verifying anything. So
Correct.
It's more or less like cookies.
Exactly, yeah, it's the same idea, yeah. So it's like a resumption. It's a secret token that lets you resume something that you did in the past. Yeah. Okay, so we call this resumption.
Same mechanism.
Yeah, same principle, yeah. So the server gives you, I'll call it a token. It's a secret for future connections. But usually we don't let these tokens last forever. Okay, so usually the shelf life on this is going to be, I don't know what it is in practice, maybe a day or two or something. Yeah, and so like after a day, it's not going to work anymore. But what it lets you do is it lets you quickly reestablish a connection itself. Yeah.
Professor, when the server gives the token?
On the first connection. So server gives you a token for future connections on the present connection. So I go to you the very first time, we've never talked before. I can't have this token. But now we do the handshake, and at the end of the handshake, you say, hey, you might want to come back and talk to me like in an hour. So here's a key, just remember it if you want. Do whatever you want, but you can remember that. Then we'll go on normal, we'll talk, we'll have our whole conversation, and then I'll go away, and then I'll come back in an hour and I'll say, here's that token again, okay? And then you're going to, so there's a little trick that we can play here. But let's say that you remember the token you gave me, right? Then we can resume right away. Now what we don't want is, we don't want servers to remember things. So we call that state. So we don't like servers to have to remember every token it gave to every individual. So what it will do instead is it will use its cryptographic key and it will max something like a message, and it will say that that's your key. And then when you give it back the token, what it can do is it can apply its key to it, and it can see that it was something it created. It doesn't have to remember it, it just knows that I must have been the one to create it because it used my key in order to create it. Yeah. So I'll write that down next class. There's a few like small details like that. But anyways, this is the sort of fix for the three-way handshake and IP spoofing. Questions about this? Yeah.
After the token expired, we can use the same token to get a new token. The refresh token.
Yeah, so that's what this is, but it has to be something that was given to you from a past connection.
Yeah, so after 2 days, for example, if you come back, the server gonna...
It's going to be like we never talked. And then you're going to go back to this, to either doing the 3x limit, yeah, and you might get retried.
So that means we cannot use the last token to get the...
You can use it, but it's a token that's created specifically for that purpose. So you don't just come back and assume the same key is going to work. I'm going to give you a key that's for that purposes only. Yeah, and you're going to use that. But I'm going to put an expiration date on it that doesn't last very long, because I'm worried about it getting compromised on your machine. Yeah.
After 2 days, I have to get the fresh and the new...
Exactly. Yeah. Yeah. Exactly. That's right. Yeah. Okay. Other questions? Okay. Good. I'll see you all next week.